Hello, my name is Jessica,
My name is Devendra Nathaniel.
and we are from Group 3. In today's video, we will present our paper titled Harnessing Deep Learning for Ocular Disease Diagnosis. On to the introduction. According to the World Health Organization, or WHO, 2.2 billion people worldwide suffer from vision impairment, and half of these cases could have been prevented if detected early. This highlights several important points. The first one is that ocular diseases are a leading cause of blindness. The second one is that the majority of vision impairment could have been prevented with early detection, and conventional methods are time consuming, resource intensive, and prone to human error. This is why we aim to utilize open source datasets and deep learning methods to assist in diagnosis. To further strengthen our research, we reviewed related previous studies. From these studies, we found different uses of various architectures with the PGG family such as PGG 16 and 19, and ResNet family such as ResNet 18, 50, and 152 version 2, and Inception 3 with relatively high accuracy of more than 90%. Now onto the methodology. For our research, we propose a comprehensive approach including data acquisition and preprocessing, model architecture, and evaluation methods. We employed several deep learning architecture, specifically VGG16, VGG19, ResNet 18, and ResNet 152 version 2. Each model will include a flattened layer to convert the 2D feature maps to 1D, and then a dense layer with value activation for nonlinearity, a dropout layer to prevent overfitting, and a dense output layer with softmax activation for classification. We utilize two different datasets, both sourced from Kaggle, resulting in a total of 7 different classes, which include eye macular degeneration, cataract, diabetic retinopathy, glaucoma, hypertension, normal eyes, and pathological myopia. For the image preprocessing, the images are converted to grayscale to highlight the texture needed. Then, we use histogram equalization, specifically contrast-limited adaptive histogram equalization or CLAHE, to enhance the image quality. To address the data imbalance from using different datasets, we use synthetic minority oversampling technique or SMOTE to generate a synthetic instance by interpolating between the selected instance and its neighbor.
Now we're moving on to convolutional neural network. There are three main layers that build a CNN architecture model, which is convolutional, pooling, and fully connected layers. Convolutional layers is whom extract the features of the images from the data set provided per certain pixels. Max pooling layers can minimize the data quantity by getting the highest feature on every certain pixels. And the fully connected layers collect all the information from the last nodes to create the conclusion and generate an output. Next, for the model evaluation, we use confusion matrix to plot the precision, recall, accuracy, and F1 score of the model we just trained. Now for the results of our experiment, we use 22 batch size and 50 epoch across all models. For VGG16 classification model, it started on 10% training accuracy with the final training accuracy of 56%. It has the overall accuracy of 60%. For VGG19 classification model, it started on 39% training accuracy with the final training accuracy of 49%. It has the overall accuracy of 40%. Now for SNET 50 classification model, it started on 31% training accuracy with the final training accuracy of a whopping 73%. It has the overall accuracy of 71%. And for ResNet 152 version 2, it started on 31% training accuracy with the final training accuracy of a whopping 91%. It has the overall accuracy of 72%. Here are the overall model comparison. So our conclusion upon seeing the result of our experiment, ResNet 152 version 2 has the highest training accuracy but have a slight overfitting. ResNet 50 has a lower training accuracy but better generalization, and balanced test accuracy, which makes ResNet 50 is the best model to train our dataset. Existing models out there achieve higher accuracy because they focus on fewer disease classes, but our model targets wider range of diseases, making classification more complex. On our future research, we would try to increase our total epochs because some model doesn't show signs of overfitting yet. We try to use regularization and experiment for fine-tuning techniques also. Last, we could try to use a larger and cleaner accurate medical dataset images. These are the references. And that's it for our presentation. Thank you for listening.